Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will look at fields. So to illustrate what a field is, let's go back to what we learned about rings. So a ring was a set of elements. Remember, those elements had to form a group under addition, but they didn't need to form a group under multiplication. In particular, in a ring, we don't have to have that every element has a multiplicative inverse. We also didn't require that multiplication was commutative, and some definitions of rings don't even require that the multiplicative identity is part of the ring. So fields just take this further. Field is basically a ring where each element has a multiplicative inverse. The multiplicative identity is part of the set, and multiplication is also commutative. So putting that together, a field is a set of elements, usually numbers, but could be something else like functions or whatever. So a field is a set of elements that form an abelian group under addition and whose non-zero elements form an abelian group under multiplication, and where the distributive law applies. Now, it's important that it's the non-zero elements that form an abelian group. If you include zero, then you'll never be able to form a group under multiplication because zero has no multiplicative inverse. So that's why we have that requirement there. So a field about which you would already know a lot is the field of real numbers. So basically, the importance of fields is that if you have a field, addition and multiplication work the same way they do for the real numbers. It's basically a set in which the axioms of real numbers apply. So we saw, for example, that Z4, though it was a ring, is not a field. Why is it not a field? Because 2 has no multiplicative inverse. For the integers modulo 4, you can't multiply 2 by anything to get 1, the multiplicative identity. So when you have a set like this, it turns out you can sometimes get weird results. So for example, we know in Z4, integers modulo 4, that 2 times 2 actually gives you 0 in mod 4. So that means you can multiply together two non-zero numbers and get 0, which is a bit surprising. That's not how it works in the real numbers. So in the real numbers, we don't get weird results like this, and that allows us to do other things. For example, in the integers modulo 4, you can't cancel because you have something like 2 times 1 is equivalent to 2 times 3 in mod 4. So you can't here cancel the 2's. You can't divide each side by 2 in mod 4. That's because Z4 isn't a field. But in the real numbers, in fields, you can always cancel like this. So that's the importance of a field. It just makes things easy. So let's look at Z5, the integers modulo 5. So I've drawn up a multiplication table. Now we know that Z5 forms an abelian group under addition, as do integers modulo any n. It just remains to be seen whether or not it forms an abelian group under multiplication, or more precisely, whether or not its non-zero elements do so. So the multiplication table allows us to see this. So we can see that if you multiply together any two elements from Z5, you get another element from Z5. So clearly the elements are closed under multiplication as shown here. We also see that every non-zero element has an inverse. 1 and 4 are their own inverses, and 2 and 3 are inverses of each other. So because each non-zero element has a multiplicative inverse, and consequently, because they're closed and there's inverses, then the multiplicative identity is a member of the set. We have here a group under multiplication. We know the associative law applies, so we have a group under multiplication. You can also see from the table here that multiplication is commutative. For example, 2 times 3 gives you exactly the same as 3 times 2. The order in which you multiply things doesn't matter. So this allows us to see that unlike in integers modulo 4, the set of integers modulo 5 not only forms an abelian group under addition, but its non-zero elements form an abelian group under multiplication. Now we also know that the distributive law applies in modulo any n, and so we can conclude that Z5 is a field, whereas Z4 is not. So in Z5, turns out we don't have any situations like this where you can multiply together two non-zero elements to get 0. Turns out in Z5 you can cancel as well. In Z5, multiplication and addition basically work the same way they do as for the real numbers. Alright, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.